Meetings. Start. Hello.
Hey.
Welcome back to physics. Let's see here. Yes. Okay. Excuse me. No. Where's our textbook? Goodness. Roger Federer at the age of, how old is he?
36.
Wins the Wimbledon for the 8th time without losing a single set. Holy crap.
Didn't lose a single set, and he kind of kicked the other guy's butt. It was like 6-3, 6-1, 6-4.
Well, in all fairness, the other guy had a serious injury too.
He did?
Yeah. He had a really bad blister on one of his feet. And tennis blisters are just as bad as it gets.
Well, if it's on your feet, especially.
Yeah. He was draining it all weekend before the match and trying to get it to some level of, but it just kept filling. Bad news. But I think that Roger Federer still would have beaten him.
Yeah.
Let's see, where am I? Why am I struggling with this? Anyway, yeah, phenomenal tennis. My goodness.
I think the only person who's beaten Federer at Wimbledon recently was Djokovic.
I don't know. Has he played at all at Wimbledon recently?
Huh?
He hasn't even played in the Wimbledon finals recently. So
Federer was in there either last year or the year before.
he wasn't even at Wimbledon last year. I don't know if he was. I don't think he played in the finals the year before, but he may have. I don't know. It's possible. I haven't followed lately very much, but for sure he has been beaten. Djokovic is a very good candidate for beating him. So is Nadal. Nadal has Federer beat all time. I think he and Djokovic are the only two players that have Federer beat all time, but still they haven't accomplished what he has. And they're both younger than he is.
I think Nadal's legacy is going to be just how dominant he's been on the clay court in the French Open.
Well, he's a power player, no doubt. All right, well, we've kind of worked very quickly through the past 3 chapters, and I believe all of those were open until, I don't know when, today?
Tuesday. Tomorrow.
So those are still open. Packer, there's some dinner there for you. Aren't you going back to work after this?
Yeah.
So you should probably eat during class.
Yeah, Federer and Djokovic faced off in 2014 and 2015. Djokovic won both.
So a couple of years ago, 2 years ago. So, chapter 8, chapter 9, chapter 10. We did finish the chapter itself. No, we didn't do 10.6 or 10. Oh, we did do 10.7. Yeah, we did all of them actually. We just didn't go into great detail. We haven't talked about the homework yet. But what we're going to do today is we're going to try to go over homework for all 3 of these chapters, 8, 9, and 10. So if you have questions, this is a good time to ask so we can cover answers to these problems. And then hopefully by Wednesday or by tomorrow, hopefully, we will have some time to start chapter 11.
And
And-
do we need to get time to schedule like the exam for
Yes, the exam is in the system. So right now it's due this Friday. Means I should probably make this chapter 10 homework due sometime this week too. We'll change that.
Because I was looking at the grade book and my heart like skipped a beat when I saw the exam grade. Because the other one, the chapter 16 kind of showed me it's a zero. So.
What's showing a 0? Oh, I see. The new exams. Now, I have said many times in this class that I feel like this class gets easier as time goes on. And I realize that students don't always believe that is the case. But part of that is because I go so much faster. You'll notice that we took at least a week for chapter 1, 2, 3, 4, and 5. Well, chapters 2, 3, 4, 5, and even 6. And then we started moving a little faster. And we've covered the last 3 chapters in just over 4 classes, I think. So just over a week's worth of classes. And if you feel like I'm going too fast, then you just need to speak up. Because really, the reason that I go so much faster is particularly in 8, 9, 10, and maybe even a little bit in chapter 7, is that the math is easier, first of all. And second of all, a lot of this stuff starts to be kind of like review. It's not really review, but it's kind of like review. For example, when we start dealing with torque, or even linear momentum and collisions, chapter 8 is almost like a little review of chapter 7. We're doing the same kinds of problems, we're just using a different equation. And so,
Yeah, chapter 8 is probably my favorite one so far, just because you have like, you pretty much just have like momentum and changing momentum.
yeah, I don't want to use the word easy, but I feel like that it's something that we can crank out pretty quickly once we understand how the system works, what the equations are all about and everything like that. Chapter 9 and chapter 10, remember the whole idea is that we've got this rotational system now that is very analogous to our linear system. And that if you use the same approach to it, which the approach was draw a picture, draw a free body diagram, label your forces, organize your forces into X forces and Y forces. And then you set up your equations. But in chapters 9 and 10, we not only have linear equations for balancing forces, but we also have rotational equations for balancing torques. Well, we just have really one balancing equation for torques in chapter 9. And then in chapter 10, we have rotational kinematics, which was essentially the same as two-dimensional or actually one-dimensional kinematics, except in rotational kinematics we use theta and omega instead of x and v and a. Instead of having distance traveled and velocity in a straight line and acceleration in a straight line, we have now rotation, angular velocity, and angular acceleration. But the equations are still the same. The way you approach the problems are still the same. You do have to sometimes convert from a linear motion to a rotational or a rotational to a linear motion. But again, that is kind of a review of what we did in chapter 6. So chapter 6 through 10, even though they're not necessarily easier and they're not necessarily review, hopefully we've presented them in such a way that they are kind of that way. So, having said all of that, let's I think what we want to do is what I want to do is I want to go through chapters 8, 9, and 10, which are the homeworks that are now due before us. And I want to do a quick review of all of them. And then by the time we're done with that, we'll take just a few minutes break, and then we'll come back and we'll take questions from the homework. So if you have worked on this homework, then you should right now be getting your questions put together while I go through this review, hopefully without losing sight of the review. If there's anything you want me to stop and explain, please interrupt. There we go. Okay, so we're going to start with chapter 8 and move on from there. So in chapter 8, we're talking about momentum, linear momentum, momentum in straight lines, which means it can have two dimensions to it because momentum is a vector like force and like velocity, and momentum is related to velocity specifically by momentum equals mass times velocity. This is a vector equation. So it can have an x momentum and a y momentum, and then you can set up equations in each of those dimensions that you can solve because momentum is conserved. In a closed system where there's no outside forces acting on the system, momentum is conserved. In fact, momentum is always conserved, but we won't get into that too much. But then we learned immediately something new, something that we call the impulse, where we have this change in momentum. We have this equation that says the net force is equal to a change in momentum over time. And if we multiply both sides of this equation by time, we got this change in momentum, which is equal to force times delta t. And that is defined as impulse. And that's where we connect the force, or all the Newton's laws equations, into the impulse equations. And it also, technically, it also connects all of the kinematic equations to the Newton's equations. But here is the impulse equation. So now we have change in momentum equals force net delta t, and this is pretty much the only equation we use for the whole chapter. We add on to this that the change in momentum is equal to mv final minus mv initial, and we also add on to this that it can exist in both the x dimension and the y dimension, so you can get two equations that look like this. But this is pretty much the only equation we use. When things change momentum, when one thing collides with another and exchanges momentum with it, then the change in momentum of one of these objects is equal to the force times the change in time. Sometimes you'll know the force, sometimes you'll know the time, sometimes you know the change in momentum, but the idea is to get something from one of those three things from the other two in the end. And they do lots of examples of this. So change in momentum really just means that your initial momentums, when you add them together, have to equal your final momentums in both dimensions. So for just a car, for just a car bumping another car in a straight line, then the conservation of momentum is momentum of car 1 plus momentum of car 2 initially equals momentum of car 1 plus momentum of car 2 finally. In two dimensions, like with the rocket ship, we're looking at this rocket ship from the side, then the conservation momentum is going to mean that after this thing gets up to the top and explodes off its top cone or whatever, then the momentum of the top cone upward and to the right is going to equal, the momentum of the rocket before it blows its top cone is going to be equal to the momentum of the top cone going upward and to the right, plus the momentum of the bottom of the ship going downward to the left. So they have to add up those momentums. You have to add up the up and down momentums to get an overall momentum that's equal to the initial rocket momentum. And then you have to add the side-to-side momentums that will equal an overall momentum that was equal to the original side-to-side momentum of the rocket. And so that ends up being two sets of equations for conservation of momentum. Same thing happens when you do things like billiard balls on the table, which we'll come to. So here's the elastic collisions in one dimension. And notice that when they do an elastic collision, we have both momentum conserved and kinetic energy conserved. So here's our kinetic energy conservation equation. Here's our momentum energy equation, our momentum conservation equation. And when we have two equations and two unknowns, we can solve them simultaneously and get both answers. That's what they do in this section. In the next section, they do conservation momentum in inelastic collisions in one dimension, where they stick together. If they stick together and become one mass, it's considered a perfectly inelastic collision, and there is no conservation of energy here. But there is conservation of momentum. The conservation of momentum is still valid, and the thing that you have to think about is what happens to the masses. In the beginning, you have two separate momentums because you have two separate masses. At the end, they're one mass because they're stuck together. So you have to add the masses together, and you have a single momentum to end with. Lots of different examples of that. The two blocks sticking together, the hockey player catching the hockey puck. Two objects that are stuck together to begin with, and then they spring apart using a spring that has the mass is one mass before, and after it's two masses, and so on and so forth. And then point mass is in two dimensions. So we have collisions of the billiard balls. Now this is the one that kind of drives people crazy, because you have a momentum initially, which is just the first ball, the second ball is sitting still, and then they hit, and then you have one that goes down, one that goes up, so they both have momentums in the X and the Y directions, right? The total momentum of the ball originally in the Y direction is 0, so the total momentum of the ball, the two balls in the Y direction, finally also has to equal 0. But an upward momentum and a downward momentum can add to be 0. So that's what you have to take into account. The real problem with this is in the math. When you get down here, you're going to end up with two equations that give you two unknowns. The two unknowns that you're going to have are going to be theta, one of the thetas, and one of the velocities possibly. You might have other ones. But in this example, I believe it is theta and velocity. And to solve for that theta, you have to get to an equation like this, combining the two equations so that you're dividing a sine theta that you don't know divided by a cosine of theta that you don't know. Then you get a tangent theta equal to a bunch of stuff you do know that you can plug in and get a number. And then you can take the inverse tangent to get that theta that you don't know. Once you know that angle that you didn't know, you can plug it back into one of the equations for the conservation of momentum in either X or Y and solve for other things that you don't know. But that's the big trick, is solving for that theta. And then we went into rocket propulsion, where they gave us this equation for the acceleration of the rocket and the velocity of the exhaust, the change in mass or change in time, which is equal to the ejected gas mass. So that's equal to the amount of gas that's ejected over time. Then you have, of course, the mass, the original mass of the rocket, and the mass of the rocket itself without the injecting gas, and then gravity. So that's an equation they give to us that comes out of some calculus, but we can make use of it. And that's chapter 8. I think what we'll do is take just a short stop right now for you guys to look through your chapter 8 homework and decide if you have any questions about it. Okay? So I'm going to leave you for about 4 or 5 minutes. You guys decide if you have some questions on your chapter 8 homework. We'll come back to discuss those questions for no more than a half an hour, and then we'll move on to chapter 9 and 10. So
I have a question.
Just a minute, I'll be back to answer questions.
Did you check the I'm having trouble with it. You didn't have to do anything inside. Did you how did you do that? Because like it doesn't close with any so it's kind of hard to figure out. The center grounds. Like the distance from the wheel to the center ground. Okay. So the two forks are going to equal each other from. Okay. That makes sense.
Okay. So, chapter 8 homework. That's where we're at right now. I'm sorry? Shoot.
Did she say number 4?
Number 4, she said.
Yeah. That's what I was gonna ask.
So we have a rocket on the launch pad. Its engine produces an impulse of 10 Newton seconds, burns for 7 seconds. Immediately after finishing its burn, what will be the speed of the rocket? Okay, so impulse, right?
Mm-hmm.
Let me go to, actually, let's not do that. Here we go. All right. So here's our rocket. Give ourselves a nose cone, some fins. Not very good at drawing rockets, apparently. And our rocket nozzle. There's our rocket, right? Now, when I'm doing my homework problems, I draw pictures not for your entertainment, but because it really does help. I've helped everybody in this class to this point individually on homework problems, and everyone in this class kind of approaches problems the same way. They read the problem on my open math, and then they do some chicken scratch notes on paper, and then they start punching things into a calculator. Let me tell you right now that you need to stop that right now. That is not going to help you for the rest of this class. You can get away with it at the beginning. You cannot get away with it near the end because the problems are getting harder here. And you can't deal with it. You can't mess with that. You need to get rid of your calculator, get out some nice blank pieces of paper, and do the whole dang thing on paper. And don't even look at your computer or your calculator until you're done. And then when you're done, plug in all the numbers and calculate it. I wouldn't even look at numbers. I don't even care about the numbers at this point. So here's my rocket. It's going to take off in this way. They've told us they have an impulse, so I'm going to write down impulse. And I know what impulse equals. What does impulse equal?
Net force times change in time.
Force times change in time. It's also equal to one other thing. Change in something. Momentum. How many dimensions are we dealing with? Are we dealing with up and down and side to side, or just up and down, or just side to side? What are we doing? Just up and down, so it's one dimension, so we don't need to worry about splitting this into two dimensions. We'll just deal with it in the y dimension, we'll call it good, the up and down dimension. So change in momentum. What does change in momentum look like for this?
Mass times velocity.
Mass times velocity final, and then what?
Minus
Mass times velocity initial, right? So there's our equation. Pretty much the same equation we're going to use throughout this entire chapter. And what do we know? What do they give us? They give us a change in time, right? They also give us an impulse, don't they?
Mm-hmm.
That's good. All right, what do they want us to find out? They want us to find out the speed of the rocket once it stops burning. That's this one right here, isn't it? Do we know anything else in this equation? For example, do we know velocity initial? It's 0, so we know that, right? Starts off at 0. So we know some things in this equation, and we need to find one thing, which is this thing. We also know the mass of the rocket, right? Now this is a funky equation. It's got 1, 2, 3 equations in it, three equal signs in it, which means essentially that we can take any part of this equation and set it equal to any other part. Now I'm going to recommend that we take two parts where we know everything except the one thing we don't know that we want to know. I'm going to suggest we take this part right here and this part right here and put them together as an equation, which means the impulse, which is a number they've given us, we'll call it imp, equals mass, which we know, times velocity final, which we want to know, minus mass that we know, times velocity initial, which we know. What's velocity initial? 0. That goes away.
Where in the reading did it ever bring up the mass velocity final minus mass velocity initial? Is that in the conservation of momentum?
It is.
Okay.
It's also at the very beginning, I believe. I think the very beginning when it talks about impulse, that's where it also is. But it also, what the thing that it also says is it says change in momentum. And in physics, change in anything means the initial moment or final momentum minus the initial momentum, right? That's what change means. And so that's what this is right here. Final momentum, initial momentum. And then you just take the number. Now that we're done with the problem at this point, unless we're going to solve for V final. V final ends up equaling your impulse, your imp, over your mass. You solve. Now, you say, why did they give us delta T? Well, I don't know. Because they had it. That happens all the time in real life. You have information that you don't necessarily need. Right? TMI. Isn't that what that means?
So you said gravity has an impulse on the rocket. Is,
Oh, did they say we have to take into account gravity? You probably do, huh?
I did not have the same number I already put as an answer.
Oh, so that's my fault. They say that we have to take into account gravity. So if that is the case, then we have two impulses acting on this thing, right? We have the upward impulse of the. Well, let me go read the question again just to make sure I'm understanding it. Sometimes they tell you that the total impulse and that includes gravity. Sometimes they don't tell you that. See, how do I go back? I go back by sharing. Here we go. Go to share desktop. Let me check that and make sure that's what it says here. Oh yeah, it says right there, don't forget gravity will also put an impulse on the rocket. So we have to add impulses. And that's fine, that's not that hard to do. Let's go back to our thing here. All we do in that case, what happened to me? All we have to do in that case is recognize that our force here is not just the force from the rocket. So in this case, it adds an extra step to our problem. So what we do is we take the impulse that they've given us, equals F times delta T, and we calculate the force from the rocket on the rocket from this equation using that time. So we do use the time in this case. And that will tell us the force on the rocket. And then when we've got the force on the rocket, we subtract off the force from gravity, which is the weight of the rocket. That's just m times g. And then we plug this back into the equation, multiply it by the delta, by the 7 seconds, or whatever the time is, multiply it by the time again, this combined forces, to get a new impulse, which includes the impulse from the rocket and the impulse from gravity. Then we use this equation. Does that make sense? So the first step is to calculate the impulse on the rocket from this equation, the impulse from the rocket, using the delta T that you have, and the impulse you're going to calculate the force on the rocket, rather. Then you take that force on the rocket, subtract the weight of the rocket, which is mass times gravity, or the force from gravity. Then you put that combined force back into this equation to calculate a new impulse of gravity plus rocket, or rocket minus gravity, or however you want to say it. And then you plug that new impulse in down here. This will be the impulse of the rocket minus the impulse of the gravity. And then you solve for velocity final. So essentially it just adds another step to it. So look, it wasn't TMI after all. We needed that time. That's G. Force is equal to mass times G. So it's the mass of the rocket, it's the weight of the rocket is what gravity is doing, right? So it's mass of the rocket times g. All right. What other chapter 8 questions do we have?
Question number 7.
Question number 7.
Yeah, I'm gonna ask that too.
Okay, question number 7. Okay. Ugh. My stomach is not feeling well today. Okay, so we have shopping cart. We have kid in shopping cart. That's before. After, and the whole thing's rolling, right?
Mm-hmm.
So the whole thing's rolling this direction. This is our initial velocity. The kid has some mass, little m. The shopping cart has some mass, big M. And they have this shared velocity in the initial in this initial direction. Afterwards, the shopping cart is going to have some velocity. We don't know what it is. And the kid, woo, jumping out. It's going to have some velocity in the forward direction. We know that much. Velocity of the kid. Right? Now, what things do we know? We know the mass of the kid, I assume, the mass of the cart. Do we know the initial velocity of the cart?
Yes.
Do we know the final velocities of the kid or the cart?
Kid.
The kid. Do we know his velocity relative to the ground or relative to the cart? Relative to the ground, okay.
Does he? I think it's towards the ground. To the
Yeah,
ground.
if they don't say it's relative to the cart, then it's relative to the ground. Okay, good. So what's the relevant equation for this? They haven't given us any forces, right? Or any times. So the relevant thing is that the change in momentum of the system is equal to what? 0, right? Before and after are equal. So I said this is the same equation as before, but it's a slightly modified one. What this is that the momentum initial equals momentum final. So what's our initial momentum? How many separate objects are moving when we start? 1. Right? Because the kid is part of the cart. Be one with the cart. So the mass of this total object is little m of kid plus big M of cart. That's our object that has momentum. The velocity of that object is VI, the initial. How many separate objects do we have at the end?
2.
We have mass of cart times velocity, which we don't know, plus mass of kid times velocity of kid. Now the beauty of this is that it is a vector equation, so that if we get all the velocities correct, let's say that we're going to consider this to be our positive x direction, then the velocity initial is going to be positive, so if we plug that in as a positive number, and the velocity of the kid final, if he's moving to the right, that's also positive, then this equation will tell us whether or not the cart's going backwards or forwards just by telling us whether v is positive or negative. And it could be either one, right? Depending on the initial velocity and the mass of the cart and the mass of the kid. So, in the end, you're solving for this v question mark here, and that solution looks like this: v question mark equals M plus big M VI with parentheses. It's really messy today. Much messier than usual. Sorry, minus MVK divided by big M. Right? That is really messy. Anyway, and then you're done with your paperwork, and you can move on to your calculator. Plug in the numbers.
Does anyone else have another question?
Yeah, I'm going to look at something really quick here.
Mm.
Am I supposed to consider drafting as a
Number 4, you say? Again? Your numbers are kind of big. The first time you did this, your answer was 160, right? That's much closer, much closer. And your answer should have gotten smaller doing it this way. If you subtract off the force of gravity intervals, your answer should have gotten about half that size.
my closer value is 6.5.
Yeah, and then you multiply it by the 7 seconds, right? And then you plug it back into your equation.
I subtracted it from the force of the rocket.
And then you plugged it back in and multiplied by 0.7.
And then that was,
Or multiplied by 7, or whatever, 7 seconds, is that what it
it
is?
was 388. And then divided by 0.05.
Wait, you multiplied by,
I'll be right back, Mr. Daly.
sure. So you have 8, 7.5, 0.5. It should be, you should end up with 8 Newton seconds minus 3.5 Newton seconds in the end. So you should have 5.5 Newton seconds divided by 0.05. That's what your answer should be. Which gets you closer, but not exactly right. Something I must have failed on something.
Well, you said to take the
So did you get 1.14 newtons of force going up? That should be your impulse. If you divide your impulse by time, you'll get force. 8 divided by 7 is 1.14. And then if you calculate your impulse from gravity, which is the force of gravity is 0.05 times 9.8. That's 0.49, and then if you multiply that by 7 seconds, you'll get the impulse. That's 3.43. But I don't need to do that. So we got, what's that? There you go. Now we fixed it. Okay. Yes, go ahead, Cassie.
It's just a quick question. On number 11, when I was trying to calculate my kinetic energy loss, like I know how to calculate that, like, because you have a car in the X direction, and so you calculate its kinetic energy, and then the car in the Y direction's kinetic energy,
Yeah.
and then you take those.
So this is chapter 8 still.
Yeah.
Which number?
Number 11. Because
Yes.
the final kinetic energy when they collide is going to be the two masses times the velocity that we calculated.
That's right, because they do stick together.
Right.
Then they become one mass. And
So then you take the initial, like the two
separately
together and divide it by the final, or the collision one, and take that times 100, right?
To calculate the percentage lost, you need to calculate the total that you had to start with.
Right.
And then you calculate what you had at the end, and then take the total that you started with, subtract what you had at the end, and put that over what you started with. So it's kinetic energy initial minus kinetic energy final over kinetic energy initial to get the...
Okay.
So you add... Sorry, go ahead.
Okay, maybe that's what I was missing. Okay. Okay.
And the reason they're asking you to do that is to show that the kinetic energy is not conserved.
Mm-hmm. Not inelastic.
That's correct.
I don't know if anyone else had trouble with number 9. I got the impulse, but I couldn't figure out the velocity.
Okay, once you have figured out the impulse, then you can go back to this equation for the velocity. So this is the equation. Impulse
the math.
equals force times change in t, which we're not going to need right now. But it's also equal to the mass times the initial or final velocity minus the mass times the initial velocity.
Oh,
right?
I didn't see the mass on top of the graph. I didn't see they gave us that mass.
Yeah.
Okay, that makes sense.
So then you can solve for one of those velocities if you need to.
Okay, thank you.
Yep. Any other chapter 8 questions?
If I have any, I'll just message you.
Packer, did you say you had?
No, I think
Chapter 8 is good? Okay. Moving on to chapter 9. Let's do a whirlwind of chapter 9 here.
I felt like number 9 or chapter 9 was a lot easier for me to understand than 8.
Well, that's good, because that is not always the case.
Reverse for me, I'm struggling with the torques.
So torque is to rotation as force is to linear motion, or something like that. So before,
Torque is rotational force, basically, or?
torque is the name that we give to a force at some distance from a point which causes a rotation, which could cause a rotation about that point. It is the name that we give to that, yes. And you could think of it as rotational force, but it's not really a great definition for it in the end, but you could think of it that way. Remember when we were talking about forces and Newton's laws and net forces and things like that, and if there's no acceleration, then there's no net force, right? And that means that the net force has to equal 0, and that's an equation we can make use of, because an equation is something we can solve. So you could split the original net force equation, we could split into x and y dimensions, but remember also that this always assumed that our forces were all acting on a point. It was assuming that the things that we were acting on had no shape or size, they were all point cows, right? This is a really good time. Did I tell you guys about the spherical cow joke? Or the spherical horse joke?
No.
So this is a really good time for a really dumb physics joke, which Paco has heard too many times in his life. But there's this horse racing guy, and he wants his horse to win the derby. And so he goes to some people to get some help. First person he goes to is a biologist. And he says, I want you to figure out a way to make my horse win. The biologist says, oh, no problem. I'll go work up some supplements and some medications and some things like this, and we'll make it happen. And then the second person he goes to is a biomedical engineer. And the biomedical engineer says, no problem, I can help you out with that. We'll do some bracing, and we'll do some splints and some other things that will strengthen up his legs and all these different things and all these different ways, and we'll do some exercise, and that's great. The third person he goes to is a physicist. Physicist, no problem, I've got some great ideas about this. So they all come back after about a week, and the biologist says, well, here's some hormones, and here's some anabolic steroids, and here's some other things. It's going to be the fastest horse. And then the engineer says, well, here's a training regimen that we're going to put your horse through that's going to involve all these robotics and all these different mechanical devices and other things that are going to make your horse the strongest, fastest horse you could ever have. And he goes to the physicist, and the physicist says, well, first, let's assume that you have a spherical horse. Right? Physicists always assume that the simplest possible scenario. And there's a good reason for that, because everything but the simplest possible scenario is impossible math. And even the simplest possible scenario, as you guys are figuring out, is really hard math. So physicists love to make things extremely simple. We love using things that are frictionless. If they always make a joke that if physicists opened a store, they would sell things like massless strings and sizeless particles, point particles, and spherical horses and frictionless materials and all these things that don't exist that make physics possible. So anyway, we've been treating a person, for example, as if they have this point at their belly button where all their mass is. And it's not a bad approximation as long as the forces are acting through that point. But as soon as they don't, the person falls over. And then you have things like torque and rotation. and things get messy. And so we have to start, stepping into the real world eventually, so we do. Instead of assuming that a car has just weight pulling down on it and normal force pushing up on it, we assume that it has one normal force at each wheel where it contacts the ground, which is actually where the normal forces are, one at each wheel. And here they're even showing that they're all kind of equal, and that's not necessarily true. In cars, that's never true, actually. They're always unequal. So even this thing here that says force applied, where the wheel applies this force to the road and the road applies a force back, that's not even all that real. The force is not applied at single points, and so it's very difficult to represent them with single arrows. But since we're not doing calculus in this course or extreme calculations in this course, we can't deal with that. Now here's an example of this equilibrium, where you have two linear forces acting on each other, and they're lined up with each other, so they're acting through the same point. So this hockey stick isn't going to accelerate, and it's not going to rotate. But if you do the same two forces and you offset them like this so that they're not acting along a straight line, not acting through the same point, then all of a sudden this thing may not move anywhere. In other words, its free body diagram still has the forces adding to equal 0. It may not take off into the next, county, but it might rotate where it is. And that is where we have to take into account things like torques. Torques are forces that act off center or off a distance from a point, and then can possibly cause rotations. So we treat them a little bit differently. And the reason we treat them differently comes down to this whole idea of opening a door. Remember that when you're opening a door, well, let's go, here we go. Remember that when you're opening a door, it's easiest to open the door if you push with a force 90 degrees to the door at the door handle, or close to the edge of the door that's part of the edge that opens. However, if you go closer and closer to the hinge, it gets harder and harder to push, which means you have to push with more force to get the same rotation. That's why we deal with forces that are cause rotation differently, because they behave differently. If this was just linear motion, it wouldn't matter where you pushed it. It would just accelerate if there was a single point particle, but it's not. It's a door. It has shape, it has size, it has geometry, like the real world. The other thing that changes, not only distance from the turning point, but also the angle with which you push matters with a door. If you push 90 degrees, it's easier than if you push at some oblique angle. So we do have to treat it differently, and the difference is in this equation. The torque is the thing that we're going to call this turning force, you could think of it as, and it's going to be equal to the force. You're going to put the force is going to be part of it, but also the distance to that axis is going to matter. That's this R. R times F. But also the angle matters. So the angle between R and F is theta, and so it's RF times sine of theta. And that's what matters. Now when you start doing equilibriums again, where we're adding forces and canceling them out, making sure that everything adds to 0 so that we have no acceleration, we also consider now no rotation acceleration. We don't want it to accelerate rotationally either. So the torques have to add to equal 0 in that case. And in this case, that's exactly what they use to balance out these kids on the seesaw. The torques add to be 0. When they add to be 0, that means that the torque from the one kid has to equal the negative of the torque from the other kid, and then you can set them equal to each other and solve. And when you do that in this case, you can calculate how far away one child is if you know both their masses and the distance of the second child from the center. And that, in a nutshell, is this whole chapter. We're going to just do different examples of it. Stability, we talk about stability where we have this, what did they talk? They said stable equilibrium and unstable equilibrium and neutral equilibrium. So there's three types of stability you can think of it as. And the stable equilibrium is the one where the where if you push it a little bit off axis, it falls back to its original. The unstable equilibrium is the one where it's balanced, and if you push it even a little bit off, it all falls all the way off. It's balanced. And then the neutral one is the one that can't ever really be stable or unstable. It's just there. Then we talked about how that changes with different things. We didn't really do much with that in the homework, I don't think. But we did do a lot with adding torques together to get static equilibrium. Where all the forces add to zero and all the torques add to zero. Make sure that your forces add to zero in both dimensions. You're still drawing pictures, you're still drawing diagrams, free body diagrams, but in addition to free body diagrams, you want to draw a regular diagram so that you can see distances of forces and angles of forces at those distances. Because eventually you'll want to add those in as a sum of the torques, or the net torque. Now in this case, they talk about the net torque clockwise equaling negative of the net torque counterclockwise. Where counterclockwise torques are considered clockwise, are considered positive, clockwise are considered negative. That's essentially the same thing as all the torques add to zero. So if your torques would cause a possible clockwise rotation, you plug them in as negatives. If they would count as a possible clockwise, torques that would cause a clockwise rotation are negative. Torques that would cause a counterclockwise rotation are positive. Then you add them all together to equal zero, and that's an equation that you can usually solve to get something you need to know, an angle, a force, a distance, whatever. But then you can also use those in conjunction with the forces in the y direction and the x direction. In this case, they're using the y direction. So they have two equations, they have two unknowns, and they're able to solve for both unknowns because they have enough equations to do it. And that is that. It comes down to just doing that over and over and over again in this chapter. They talk about simple machines, which are the same kind of thing. They're just balancing torques, but they do give us another equation for calculating mechanical advantage, which is the force out over the force in. But besides that, we're pretty simple. Then they did for muscles and joints, which is just an application for like our lab. Now, what time is it? Okay, we're going to give you another few minutes to look through your homework in Chapter 9, decide what questions you have. I'll be back in a few minutes, and we will start Chapter 9. Okay, who's got a question about chapter 9? Yes, sir.
Coincidentally, number 9.
Number 9. Kitty cat.
Yep. So the way I was approaching it, and I got a number that doesn't make sense because the number that came out the back end says the cat can be farther than a can of sardines is and still have a balance.
So this one is a bit tricky. Since it was such a short assignment, I didn't think it was too bad to have this be tricky. Let's see, they give us the board length. They give us the weight of the board. They give us that it's 2 meters beyond the end of the pier. They give us the weight of the can, or the mass of the board, mass of the can, and mass of the cat. They want to know how far I can get out before it falls in the water. Okay. So let's tell you, like, this will be fun. Where'd my whiteboard go? There it is. Okay. Okay, so here is our pier. Whoops. Here's our pier. Here's our board. And our cat's going to be out to about here. We'll say cat can. Okay, so the first things first is to start drawing some forces. Okay, so when we're dealing with objects that have length and weight to them, kind of a linear object like a board that's length is spread out along its length, we're going to assume that it is spread out evenly along the length. So that, you know, this 5 kilogram board is not 5 kilograms acting right here, you know, with gravity. It's acting at the center of the board.
So we're assuming its entire weight is at the center, or that it's spread out?
We're assuming that the weight can be treated as if it is acting at the center of the board. Okay, because the weight from gravity doesn't cause the board to rotate. So we could assume two things: either it's acting at the center of the board, or it's acting evenly all the way across the board. Well, acting evenly all the way across the board, we don't know how to deal with. That's calculus. We do know how to deal with center of mass of the board, or the center of the board. However, we've got this one little problem that is two board situations. We have one board that has a normal force acting on it, one board that doesn't have a normal force acting on it. This board on this side, the right side, has a normal force acting up, which we will consider to be halfway. So let's consider the board to be two lengths. The length that is supported and the length that is unsupported. Okay? And the length that is supported, we're going to cut right in half, whatever that half is. And we're going to pretend that that has a force of the weight of that part of the board only. The weight of the supported part of the board acting in the middle of the board right there. And there's also a normal force acting upward on the board there, which is equal to the weight of the supported board. Okay? Well, there's a normal force upward that's not necessarily equal. Actually, it's not necessarily equal, but there is a normal force. Then we have other things. We have the weight of this other board. So this is the weight of the unsupported part of the board. Now, these weights are going to be different. If this board is 6 meters long and this is 2 meters and this is 4 meters, then 2/3 of the board's weight is going to be on the right side and 1/3 is going to be on the left side. We have to split up the weight accordingly. But we also have the weight of the cat. Now, the weight of the unsupported board is at half of the length of the unsupported board. And the weight of, from this point, this is where I'm going to consider, well, I'm actually going to probably consider my point of distance to be this point right here, so I don't have to deal with these two forces. So I'm going to calculate all my torques from this point. You don't have to. It's up to you. I'm going to call this my point of interest just because then it eliminates, I don't have to calculate torques from those two forces, right? Of interest. But it doesn't matter where you choose it. You can choose it wherever you want. But then I'll calculate everything from that point and move on from there. And they want to know how far from the edge the cat can go. Is that what they want to know?
Yeah.
Okay, so they want to know this distance here, which we'll call this distance x, but the distance that the cat is from this point is half of L sub s plus x, right? So we have to keep that in mind. And then the length of the can of food is the length of the unsupported board, which they've given us, right? Now we've drawn our picture. Oh, we need the force. We have the weight of the can right here also. Weight of the can. Now we've drawn our picture that has all of our forces except weight of cat. Let's put weight of cat here. What? Does the can have what? No. Yeah, there's a normal force between board and can, but that's internal to the system. So we're only talking about forces that are affecting the board, that are affecting what the board is doing. So the can board interaction is not going to change anything, but everything else will. So, now what do? Well, we have some equations to deal with. We're only dealing with forces in one dimension, y, right? We're not dealing with any forces left and right, so I'm going to call this my positive y direction. And then that means that the sum of the forces in the y direction has to equal what? If this thing's not going to be falling over.
If it's not moving, it's 0.
It's 0, right? So the sum of the forces equals 0. And what are my forces in the y direction? Well, we have the weight of the can, and that's negative. I'm going to put that on there as negative. And we have the weight of the cat, weight of the kitty. And we have the weight of the unsupported board. Right? And we have the weight of the supported board. And we have the normal force. That's positive. Okay. The two things we don't know, well, the one thing we don't know in this equation is the normal force, right? We could calculate the normal force from this equation. But we don't want to know the normal force. We want to know the distance to the cat. So this equation is not going to help us unless we need the normal force in our next equation. What's the other equation for equilibrium that we can use? The sum of the what? Torques equals 0, which means that we're not going to have any rotational acceleration, right? Now, positive torques, negative torques, right? Positive torques, negative torques. So here's my, let's see, do I have any, maybe I shouldn't measure it from here. Yeah, I don't think I'll measure it from here because I'm going to need to know, let's see, negative, these are all clockwise torques over here, around, the only, I mean counterclockwise, yeah right, counterclockwise. Which means we'll get an equation we can't solve if we do it from here. We'll do it from here. Okay, so then we get the weight of the can, so all the positive ones are the counterclockwise. This one, this one, this one, and the normal force. So we have the weight of the can, but remember it's not just forces. It's forces times
Distance?
Distances times the sine of the angle, right? Well, the sine of these angles is all 1 because it's all 90 degrees, right?
So that we don't have to worry about
We don't have to worry about the angle. We can just write force times distance and worry about the sine. The counterclockwise ones are all positive. We'll write those first. And the distances. So the distance from here to the end of the board is whatever it is. It's the length of the unsupported board times the weight of the can. And then we have plus 1/2 the length of the unsupported board times the weight of the unsupported board. And then we have our distance x times the weight of the cat, right? And then we have the normal force plus the normal force times the distance, the length of the supported board. And then we subtract off all the other ones, which is just the other one, which is just the weight of the supported board. So it's the length of supported board times weight of supported board. Okay? Now, over in this equation, when we solve for normal force, we're going to have a value that we can plug in over here. And then we can solve this equation for x, which is what we want to know, because we know everything else. Yes?
So can you explain the equation?
Which equation?
The equation you just laid out?
Second one? These are all the torques.
Like, I just think
So-
understanding each one.
The torque, the first torque comes from the weight of the unsupported board. It's a counterclockwise motion torque, so it's positive. And you have to multiply the distance from, this is going to be, we changed our point of interest to here instead. So it's the distance from the point of interest to there, which is half, sorry, I went to the cat first. So it's the distance from our point of interest to the weight of the can, sorry, weight of the can, not the cat, times the actual weight of the can, right? So it's distance times force. The next one is distance, which is half the length of the unsupported board times the weight of the unsupported board. And then we had the distance to the cat times the weight of the cat. Then the distance, now we're going this way, the distance to the normal force, which is half of this distance, times the normal force. And then the distance out here times the weight of the supported board. That make sense? We need those things to balance.
Mr. Bailey,
Mhm.
would it be the length of the supported board, wouldn't that be 1/2? It's that second to last term.
Oh yes, both of these are 1/2, so 1/2 the length of the supported board, the weight of the supported board.
What's the last one? You have the length of the, oh,
This is 1/2 the length supported board to the weight of this force right here.
okay, because the weight is negative because it's going
Yeah.
to be clockwise.
That's correct.
What if the part of the board that's not, that part of the unsupported part of the board isn't directly half of the
That's why we split the board into two pieces, right? We split the board where it hits the end of the cliff, and we said the half that's sticking out is the unsupported part. The half that's on the ground is the supported part. So we made two separate boards. We split up the mass
Proportionally, right?
proportionally.
But if it's unproportional.
It's never in proportion because it's physics. No, so if you have 2/3 of the board sticking out, or 1/3 of the board sticking out and 2/3 not sticking out, then the 2/3 of the board that's not sticking out is going to have 2/3 of the mass of the total board. That's proportional, right?
Did we also do
Number 10. Read in the window washer. Okay, this one looks like it would be more complicated, but it's actually simpler than the last one. It's the same problem. You just have a sum of all these forces and torques.
I got the tension part of it, but I was struggling to find a way to calculate the distance. How much distance he'd have until.
So tension, this is what you got. You got the weight of the board acting in the middle. You have tension acting up here and tension acting up here. And then you have the man. Where do they want to know his distance from? The center of the board or one of the edges?
the edge? It says that the rope on the right is damaged. It can only support a certain amount of
And they want to know how far he needs to be from which side.
how far he can be from the right, or how close he can get to the right before it breaks.
So if you want to know how close he can get to the right before it breaks, then we should measure everything from the right side.
Okay.
So we'll use that as our point of interest. Right? We have the weight of the person right here.
We don't have to worry about the normal force because that's internal, right?
No force, the normal force of person and board is internal to the system. You could treat this as if the board was just really heavy at that point. That's why it's internal to the system, right? Whereas if something external is acting on the board and actually causing it to do something, then it's a problem. But anyway, so this is the weight of the person, tensions from the ropes, and then the weight of the board. And the equations are the sum of the forces equals 0 and the sum of the torques equals 0. In this case, we only have forces in the y direction. Then. We'll choose our y direction to be up, our positive direction to be up. And so it's sum of the forces in the y direction. What does it look like?
0.
Yeah, it's 0 because this thing is not accelerating. But what is the first force? Tension plus another tension because there's another one going up.
And
Minus
the weight of the
weight of the person plus the weight, or minus the weight of the board. Right?
So using that, we can figure out the tension of the other rope and support. Because we know everything else, right?
Oh, these are, oh, right, they want these to be different tensions. So we need to do this tension left and tension right. We do need to split these up. Tension left, tension right. You would only put them as the same tension if it was the same tension. We don't know that it's the same tension. But anyway, tension left, tension right. Now they've given us some of these things, haven't they? What have they given us? They've given us the weights. They've also given us one other thing. Didn't they give us the maximum tension that the one on the right can handle?
Yep.
So from this equation, we can calculate the tension that is going to be left on the left side. That's going to be on the remaining tension that the left side is going to have to support in order for this to happen, right? However, it doesn't give us any distance. But that's okay because we're going to calculate the distance in the next equation.
It said that when the board was 500 and the line's 500, so it gave us the
Yeah, it gives us the length, but we haven't used it yet. So now the sum of the torques equals 0 also because this thing is also not going to rotate, right? So the torque from the left side tension, this is our point of interest, POI. So how far is the tension from the left one? It's the entire length of the board, right? We'll call the length of the board L. And it's going to be L times tension left. And is that one going to be positive or negative? Is that going to cause a clockwise or a counterclockwise rotation?
In which way?
From this force right here, is this one going to cause A clockwise or a counterclockwise rotation around our point of interest?
Clockwise.
Clockwise, so is it positive or negative?
Oh yeah, it would be clockwise, sorry.
So negative, right? It's negative because it's clockwise. It would go up around this way. So it's negative because it's clockwise times the tension on the left. And then we're going to put our next one in from the weight of the person. The weight of the person, clockwise or counterclockwise?
That would be counterclockwise, so it's positive.
Counterclockwise, so it's positive, so we do it plus. What's the distance to this person? That's what we want to know. That's our x, right? Plus x times the weight of the person. Mass times gravity of the person, right? Then the next one, the next force is the weight of the board. Also counterclockwise. Plus weight of the board. Well, times the distance, which is 1/2 times L, right? L over 2. Weight of the board times the length over 2 for the weight of the board, torque. And that's also a positive torque. And then what's the last one? TR times distance what?
0.
0, which is 0. Which means we're done with our equation, right? Now the great thing is from this first equation, you're going to be able to calculate T sub L. And then you'll be able to plug that into this second equation. And then you'll be able to calculate X because you know everything else. Ta-da!
So, when I was plugging the numbers through that first equation where you have the sum of the forces, I ended up getting a negative number for the tension on the left row.
Did you put in negative numbers for your weight? Or did you put in negative G's for your weight, or just G is 9.8?
Just G's.
Just 9.8?
Yeah.
So you got a negative weight, a positive, what's your TR on the right side?
350.
350. Negative.
So do I need to make those 9.8s negative?
No. And it gave you a what? It gave you a negative tension? That's really weird.
Should I just put it in and see what it does?
Sure. Your TL should be hugely positive for that equation to work out. What was TR again?
350.
What's the weight of your person?
73 kilograms.
Times 9.8.
Yeah, which I got. Yeah, 75.6.
So you should have, and what's the weight of the board?
The weight of the board is 12 kilograms.
So you should have 75, 750, 870. No, you definitely get a positive number. You must have plugged it in your calculator out. Because you're going to get 870, you're going to get 350 minus 870. So you're going to get minus 500 something, 520, and then you're going to add that to the other side.
I got my signings all fit for that. Because yeah, I see what that is now.
Okay. Any other questions on that one?
I'm still struggling with question number 8. We're up there.
Okay. Anyone struggling with this one still? Are we good with number 10?
I'm just
No, number 8 was the one that I was going to go in and do and never did because I got sick.
I actually figured that one out.
Okay, so tell me how you figured it out. Because Packer and I were trying it, and the way that I was going about it, I was needing one more angle or one more distance.
It's just the same way with like I said,
In the actual book, there is an example of this that it shows you how to do it.
But that example isn't S, but it's different though.
Let's go look at the book really quick just for kicks and giggles. I know it happens to be in the machines part because I was just there. So this one here. So the wheelbarrow, this is the mechanical advantage of a wheelbarrow. Um,
That's not how we do it.
Now this is a very different kind of problem though. Well, let's so the way that I was doing this, I was assuming that the center of mass of the soil being 1.1 meters from the wheel was 1.1 meters from here to here. Let's go back to my, there we go. I was assuming that it was 1.1 meters from this point to this point, which means that you would have to either know the height or the horizontal distance or the angle there, which you don't know. And so if they're saying that it's 1.1 meters from here to here, then I can do this problem.
I thought it was going at a diagonal from there.
What did you do?
I just put, like, I just did the torques and with and
So, but you used the 12-degree angle for both. So apparently, if you use the 12-degree angle for both and those distances, Packer,
Okay.
and balance the torques, then you're good to go.
Alright.
That is what I did.
So yeah, that's a poorly worded question. I suppose I should go in and fix it as well.
kind of funny that I didn't do that, 'cause usually I'm the one who thinks it.
No. It's all right. Any other questions from chapter 9?
Mr. Daly?
Yep.
On the number 10, is it on the part where it's how close can you get to the board? Is it good or bad thing if the negative number popped out the back? Because since wouldn't it almost be like we're considering towards the left is negative, so that's how far away you can be from it?
Where are you measuring all of your distances from the far side, right?
Yeah,
Yeah, negative would be wrong.
it would be wrong.
Yeah. Because that would be on the right side of that. It would be to the right of this one right here.
So I'm saying you can get to the right of it before. That first, when you're figuring the first torque, that's the torque from the 10, that, from that left row. That would be it's just the left.
Wait, you're measuring torque from the right rope, right?
Yeah, because that's the
Okay.
weakened row.
Yeah.
So, since that's a torque that's going up, it's clockwise, which makes it negative. And so you have the length, you have the negative.
The length times the force of tension, and you put
down
a,
from the previous equation,
and you
right?
slap a negative sign on it.
Okay, and that gives me a really good number. I think that's where it's coming from, maybe.
Should be. Well, you don't know that number. You're going to solve for that number. You solve for that number in the y force equation.
I was wondering, because I was looking in that, that was the correct, isn't that the correct unit for that?
Yes. Send me a message. I'll go in and check that. Try just NM without the times.
That's what I did the first time.
Still didn't work. I think I was having trouble with that one. And I couldn't figure out what I was doing. Go ahead and just send me an email. All right. So, unless we have objections, I'm going to move on to chapter 10. Do we have any objections? Okay, now chapter 10 looks really crazy big and we cover a lot of stuff in it, but really, chapter 10 is kind of a review of something we've done before, just in a different situation. We've done things like kinematics. We've done things like dynamics. We just did them in linear motion, not rotational motion. And there's this big back and forth between linear motion and rotational motion. Sometimes you're only dealing with rotational motion with the equations and you don't have to go back and forth. But sometimes something is got a rolling wheels, but it's also moving forward in a linear fashion. So you have to use both. You have to go back and forth in between them. But in a very simple way to kind of relate these things is to make a little correspondence. So here is the correspondence. In linear, this is a good idea to write this down. Somewhere. There are a couple of places in the book where it is found, but maybe not quite as compact in one place as this is. In the linear direction, we used things like x, y, z. Maybe we didn't use z much in this class. But we used these variables that represented distance. But when we're dealing with angular stuff, what do? We don't deal with distance. We deal with angle. We use theta, right? Because we're just rotating. In the linear, for velocity, we had v. We had v sub x. We had v sub y, right? But in the angular realm, we had omega. Now, right away, there is some correlation. There's some correspondence here. If you have, for example, a motorcycle or a wheel moving along in a linear fashion, it's moving along with a velocity in the x direction. It's also rotating along in angle, in a theta kind of direction. Then the relationship, a theta and an omega, right? This is an x distance and a vx velocity. This is an angle theta with an omega velocity. If you're going to relate these two, how do they relate? They relate by the radius r, right? You multiply the angular by the r and you'll get the linear. And so the distance along the edge of a circle, the arc length along the edge of a circle, is, you could call it x, the tangential x, or we usually use s for it. It's a curve along the edge of the circle. But that is related to the distance as you travel across the ground. It is the same distance, actually. And so r times theta becomes x. And for the angular speed to relate to the linear speed, it's r times omega equals v sub x, or v sub t, with the tangential velocity.
To get from one to the other, you multiply by r.
To get from angular to linear, you multiply by r. From linear to angular, you divide by r. right? The next one is acceleration. In linear, of course, we have acceleration in the x direction, we have acceleration in the y direction, but in angular we have alpha, the angular acceleration, rotational acceleration. In linear, we have things like force. Force equals mass times acceleration. It's a vector. These are all vectors.
In angular, you have torque, right?
In angular, you have torque, and it doesn't equal mass times acceleration equals this new thing, which is related to mass, but also related to mass distribution, which we call, you guys remember what it's called?
Inertia.
The moment of inertia, right? And it's I times alpha instead of mass times acceleration. It's I times alpha. Right.
What was the formula for the moment of inertia?
And the moment of inertia has a bunch of different formulas. See the book. There's a table in there for depending on the shape, depending on how it's.
Oh, yeah, that was like the 2mr squared.
That's right. There's almost always an mr squared involved somewhere. See the table of shapes. And if you have multiple items that are rotating all around, oops. Multiple shapes that are all rotating around the same axis, then you can just add all the different eyes together, just like if you have multiple masses moving along together. You can add them together. And then over here we have momentum equals mass times velocity, vector. And over here we have angular momentum. We use L, also a vector, equals I times omega as a vector. And then this one had the right-hand rule involved, right? You turn your fingers of your right hand in the direction of the rotation of an object, and your thumb will point in the direction of the angular momentum, which is always conserved.
So if you have like a wheel rotating like this,
That's right.
you put
Curve your hand around that
around
direction.
it,
Right hand.
put your right hand there, so it's rotating like this.
That's right.
Its angular momentum is that.
That's correct.
Okay.
Then there was things like kinetic energy. Here we have kinetic energy. Remember, kinetic energy is not a vector. It's 1/2 times mass times velocity squared. Well, what is it for angular rotation? What's angular kinetic energy? 1/2. What do we replace mass with? We replace mass with moment of inertia.
Times the angular velocity,
Omega squared. Right? So those are all the changes. Well, they're not all of them, but that's the vast majority of the changes. Those are the ones we've learned. But there's also kinematic equations for angular momentum, for angular velocities and angular distance or angular rotations and things like this. There's all the kinematic equations. So in the linear kinematic equations, we have equations like I don't know, pick one. Velocity final equals v naught, the initial plus acceleration times time. Well, there's another equation like that in the angular that looks like omega final
plus alpha times time.
plus alpha times time.
So basically, you can just kind of take the equivalents.
That's right. Once you understand how these relate to each other, then all the problems are the same. The only challenge is when you have a problem where you have both linear and rotational kinematics going on. When you have a rolling wheel, a car with rolling wheels. Just think, rolling wheels is what it comes down to. Things that are spinning but also moving forward. They will have aspects of both that are, if it's a wheel that's causing that forward motion, then there will be the relationship between the rolling of the wheel, theta, and the distance the wheel travels, x, that is related to the radius of the wheel. The bigger the radius, the more distance you're going to go for a certain rotation because r is bigger, right? And that's how it goes. And that pretty much is chapter 10. That's the whole chapter 10 right there. So let's go through it really. Sure. You're welcome to take a picture of it. Might want to get up closer. I think that what I'm going to do next year, next fall, is I'm going to have a iPad at each table for each group of students.
There's actually this whiteboard on a web browser that you can actually share.
This one you can share. So that's why I'm going to use it. But not only that, but also you can capture things on it and keep them. So, okay. So chapter 10, this is it. So angular acceleration we start off with because in the previous chapter we talked about angular velocity and the relationship between linear velocity and angular velocity. Now remember, the linear velocity here is the velocity on the edge of the angular circle that you're dealing with. So it has to do with a distance r, a radius r. But it relates to, if it's a wheel that is turning on the ground and causing forward motion, it is related to linear velocity as well. So if you're given an angular velocity or you're given an angle and a time, you can calculate an angular velocity. Then you can calculate a linear velocity in that situation. And that's what this multiply by r, divide by r thing is. To go from angular to linear, you multiply by r. To go from linear to angular, you divide by r. Okay, and they demonstrate that here. The acceleration. And here they begin developing the kinematics. So here's one of those tables I was telling you about. So, here they begin developing the kinematics. V equals V naught plus AT. And if you replace V with R times omega, and V naught with R times omega naught, and A times T, R times alpha times T, you're just multiplying by R to go to the angular, right? Or sorry, to go to the linear. So this is the linear equation expressed as angular. And then they just divide out the R and everything, and they get omega equals omega naught plus alpha times T. That's supposed to be alpha, not A. I think that's a typo. And here's another one of those charts that shows all of those correlations. So you get translational kinematic equations and rotational kinematic equations. But you approach them the same way. You approach problem solving the same way. You write down all the things that you're given, and then you find an equation that has the things that you're given and the thing that you need to know. Plug it in and solve. You might have to use 2 or 3 equations to get to where you need to get. But you just use the same situation. It's the same kind of situations as we saw in kinematic equation, the kinematic section. Now here's an example of something that's rotational becoming linear. You have a line of wire on your fishing pole that's wound up on a coil here, wound up on the reel, And as it rotates, as the wheel rotates, some of that line comes off. And it's coming off in a linear fashion. So it comes off with an x length, a v velocity, and a acceleration. But when it's rolling, it's not behaving like that. It doesn't go a distance while it's going around. It goes through an angle. It has a theta. It has an omega. It has an angular speed. It has an alpha, an angular acceleration, right? But not only that, but it also has things like torques. You can add torques to it. You can add a brake to it. You can accelerate it by winding it one way or the other. So you start using those kinematic equations to do these problems in rotation that are also related to related linear problems. And then you go into torques. Forces are equal to masses times accelerations, but if you convert the acceleration, the linear acceleration into an angular acceleration, then your angular acceleration times r equals your linear acceleration. So that's Newton's law on the top there. This one on the top is Newton's law. Sorry, just had to make sure I was in the right thing. So this is Newton's law, but instead of a for acceleration, it's r times alpha, which is equal to a. And then they do this little trick where they multiply both sides by r, and then they divide by, they multipy both sides by r, and then they get r times f on the right side, which is a torque at a 90-degree angle. And then they notice that this is some stuff times an angular acceleration, so they call this stuff, this mr squared, they call it the rotational inertia. But that's only good for a single object, a point particle that's going around in a circle at an r distance from the center. That's really good for this example where you have this puck that's at a distance r going around a circle. But if you have other objects that are not going around, that are not just a single particle going around in a circle, they're shapes, then it turns out differently. And they tell us how it turns out here. They just give us the end result. In a calculus class, you'd actually have to calculate most of these to get them. But in this class, they just give them to us. So you use these rotational inertias, or moments of inertia, to use in the equation for Newton's law of rotation. Newton's law of rotation, again, being torque equals r times f. You also could have the sine theta if you push at an angle other than 90 degrees. So in most of the cases, we push at 90 degrees, but not all the cases. And so we get the torques. We can calculate torques using mass, distance, and angular acceleration.
So in any one it says that for most of them, yeah, since it's like a rolling wheel, and you have to have that moment of inertia. If you don't, though, you can just tack on the sine of whatever the new angle is after the moment of inertia.
I don't understand.
So you're saying that most of them, we don't have to worry about the sine because it's like a 90-degree angle, right?
Yeah, most of the problems that that we've done have a 90-degree angle, but every once in a while, for example, the wheelbarrow problem has that 12-degree angle or whatever. Sometimes you have to tack on that angle because it does depend on
For
the
rotational kinematics, we have to worry about that.
No, in rotational kinematics, you never calculate a torque. But eventually, you're going to use torques now to calculate accelerations, and then you'll use kinematics with the acceleration. And so it does matter when you start calculating the torques. Right? In kinematics, doesn't matter. You're not dealing with torques. But you do combine kinematics and forces and torques, just like we combine kinematics and forces. Because with forces, you can calculate accelerations, and then you can use accelerations with kinematics. Right? So, that's Newton's second law with torques. And then we immediately move on to angular momentum. No, kinetic energy first. So they talk about work equals force times distance. In this case, work is going to be a force times a distance along the edge of a circle because we're doing rotational stuff. Our edge of the circle distance is a delta S. It goes through this angle theta, and delta S divided by R gives us that theta. So our net work is equal to our force times delta S divided by R, which is our theta, but since we divided by R, we have to multiply by R, so we get R times F, which is a torque. And so we get work equals torque times theta. Okay, fine. Well, torque is equal to I times alpha, according to Newton's law, Newton's second law for torques. So we get work equals I times alpha times theta. And then we can start dealing with kinetic energies that look like this. Since we have omega for our angular speed or our angular velocity, then kinetic energy rotational equals 1/2 times I times omega squared. And we're at kinetic energy. Therefore, a bus rolling down the street has a kinetic energy that is linear kinetic energy, but it has some extra kinetic energy from rotating tires, rotating wheels. Anything rotating flywheel in its engine. You know, anything that rotates adds kinetic energy to anything.
So it would probably be really, like if the bus, so like if, when kinetic energy in like a situation like that could potentially be conserved where if like the bus runs into a car that's not moving, the linear kinetic energy we already talked about, the rotational kinetic energy would transfer from the wheels of the bus to the wheels of the other
So
car.
let me give you a great example of kinetic energy being conserved, of rotational kinetic energy being conserved. My brother was driving his Volkswagen Beetle, which was my Volkswagen Beetle also. It was a piece of junk. It was a 1956 Beetle that was converted into a Baja bug, so it had big fat tires on the back and little skinny ones in the front, little bug-eyed headlights, and terrible small steering wheel you could barely turn the car with, and it was a great car. But it was so old and so rickety that he was driving it down the highway in Nevada once, you know, the really long highways you see in Nevada. And as he was driving along, his wheel passed him up. And he didn't really know what to do, so he pulled over, which was a bad idea. He should have just kept driving to try to catch it. But he didn't. He pulled over, and because it was the wheel on the right side of the car and he was sitting on the left, he had balanced out the car so it didn't fall over. But the kinetic energy was conserved. He had to walk like a mile to catch this stupid wheel that kept going. Okay? And because it was not being, well, anyway, the kinetic energy is conserved in that wheel. Even it had kinetic energy before it was with the car, had kinetic energy when it left the car. And in fact, the kinetic energy, it was actually able to pass him up because it had both kinetic energy and angular momentum, but it had very little force stopping it at that point. Nothing to fight against. It had very little friction to deal with because it was disconnected from the car. It ended up going faster than the car itself. But he eventually got it back and put it back on.
All the time, I think it was my grandfather was towing the boat, like, out to the lake to go boating, and all of a sudden the boat passed him.
Yeah, not a good idea. Not a good thing. So anyway, was the boat still on the trailer?
Yeah.
Oh.
Would have been really.
So the trailer wasn't still attached to the car?
Huh?
So
Yeah,
the trailer-
detached from the car and passed him.
Yeah.
And it ran into a parked trailer.
Did it destroy the boat?
I can't remember. I just remember that my parents. The one thing my parents remember was like we had a big extended family garage sale. My parents had made money, my grandparents had made money,
I
and
bought a boat.
the garage sale money went to paying for a new trailer for the people. My parents were kind of happy that they were able to keep their part of it.
Yeah. So anyway, rotational kinetic energy. Now, that was the experiment we did where different things roll differently down hills, right? Even if they have the same mass, the objects that have the same mass will slide down a frictionless incline with the same acceleration, but they will not end up having the same speed at the bottom if they roll, because their potential energy at the top is the same, but some of that potential energy goes into linear kinetic energy and some of it goes into rotational kinetic energy. And the bigger the moment of inertia you have, the more energy you have to put in to turn it, right? That's why the ring, with all of its mass on the outer edge, lost the race, because it had all this mass that was such a far distance from the center that it had a big R, and of course, the I is equal to mr squared, right? So,
And the wooden one was able to beat it because it's more evenly distributed.
yeah. Okay. The last thing that we covered in chapter 8 was the conservation of angular momentum. And we called that L times equals I times omega, right? This gives us another equation. Conservation of kinetic energy gives you an equation. Initial equals final. So if you're in a situation where kinetic energy is conserved, it gives you an equation that you can solve. But even before that, we had equations we could solve. The sum of the torques equals 0. All the kinematic equations, all those things are equations you can solve. Anytime you have an equation, you can solve it, and that's the beauty of this. Now, angular momentum is conserved, always. Now, we say that that's true always, and it is true always, but we can calculate it, we can actually make use of it when we define a system where the forces from the outside on the system are 0. There are no net forces on the system. If there are forces from the outside, then we have to consider everything that's applying a force, and that can get really crazy. So the example here is the kinetic energy conserved when a skater is on frictionless ice and goes from this arms out spin to the arms in spin. The rotational kinetic energy is conserved. Kinetic energy rotational is not conserved. They actually calculate the kinetic energy rotational and show that it's not conserved in this case, but rotational or angular momentum is conserved. So kinetic energy not always conserved, just like normal. Momentum always conserved. In this case it is. Now, why wouldn't the kinetic energy be conserved? Anybody have an idea of what's going on with the skater? Why would kinetic energy not be conserved? Is there any energy that the skater uses to make things change?
Moving the various levers.
That's right. When we had a collision of cars and we lost energy because it was an inelastic collision of some kind, we had energy that was being lost, scattered by sound, by crunching, by friction, all these things where we couldn't recover the energy. In the case of a human or another biological creature, they can move their arms and change they can change their moment of inertia by changing their shape. But that energy comes from somewhere. They used energy to change their shape. So they're essentially adding energy to their system. Their kinetic energy increases in this situation. It's not conserved, but it increases because they put energy in by using biological energy, muscles, and things like that to change their shape. Okay? So that's very similar, except in the car when it gets lost out into the universe. In this case, the energy is being used from internal to the body to increase the rotational velocity. But still, the point being that these are not really new ideas. These ideas are old. How to solve these problems is something we've done before. We have equations, we have values, we find the equations that will give us the thing we want to know, we plug in values, we maybe solve a few things along the way to get things we need, And then we're done. Even the concepts are not really all that new. So, chapter 10. Let's see. I don't remember how many problems they gave you in chapter 10. How many did they give you?
Well, I think it was 2, it was like 16.
16 problems?
Um,
So has anybody started this?
I did a couple of them.
No.
I still had a question about chapter 9 of
You still have a chapter 9 cat question?
the cat. Yeah. I did the math and had a number that was not correct come out. I have to make it a number again. I checked it because I've been making the same error when I had a negative one. I made sure I wasn't making that error and it still is.
Okay, we'll talk.
Just put chapter 10 questions up today.
I put the chapter 10 questions up last week sometime, maybe Friday, Thursday? I don't know.
Well, it said there were no questions in the. Oh, last week.
Yeah.
Friday. Well, I clicked on it and it said there were no questions in the assessment.
I don't remember what day it was. What day was that, Packer? I think it was Friday that I put them up. Possibly Saturday morning. I don't know. I have trouble keeping track of the days in the summertime.
Yeah.
Monday, Tuesday, Wednesday, I have a tendency to remember. Only other days I don't, because I don't come to work on those days. But at some point. But it's not due till this Friday, I think. So, you got time to work on it. So right now it's 5:40. Class is over. I think, well, class is close to, what time is class over? 3:30 to 6? So it's over at 6. Class is close to over. I want to just go through these really quick so that you guys can get started on them. We will spend some time tomorrow answering questions on chapter 10 and getting ready. We need to start chapter 11. Well, let's see. We might. Let's see. Chapter 11 is fluids. I'm trying to remember what labs I can send you. You still have a motion detector there, right?
Yeah.
Okay, so I can send you a lab that you can do with the motion detector and with fluid statics. I don't remember. Fluid density, pressure, Pascal. Oh, shoot. Archimedes. We could do an Archimedes principal lab. We'll do an Archimedes lab. I can send you a lab for that. You won't need anything new except something to hold some water and some string and a force measuring thing that you've already got. So we'll do something with Archimedes principle on Wednesday. So we need to start chapter 11 tomorrow. So we'll do chapter 10 homework tomorrow a little bit, and then we'll do chapter 11 tomorrow, and then we'll do Archimedes principle lab on Wednesday. And then of course we have homeworks due and an exam. I know that it's feeling kind of crammed, but just crank through it, and I'll help you as much as I can. Remember that you can send me, I don't get a lot of emails from you guys. For my math classes, I get at least 5 or 10 a day. And they're not nearly as hard as this class. So get started on your homework early and ask questions early, and I can get back to you with a whiteboard example or something explained in the email or something. But as quickly as possible. Okay. Let's look through the chapter 10 homework really quick. And this one, it's artificial gravity. They're giving you the centripetal acceleration. They want you to calculate.
Centripetal and angular acceleration are the same, right?
No.
Okay, what's the difference?
Centripetal acceleration, remember, is the acceleration towards the center. So this is a little bit of a review.
Okay.
So this one is a review problem from the, and I put quite a few review ones in so that we could remember some things about angular motion, rotational motion rather. So that was just a review from a previous chapter, just to get us started with rotational stuff.
Okay.
This one, however, is not review. This one, well, it is kind of review, but it also is a little bit related to what we're going here. We have diameter of a propeller, we have the RPM, so we're going to convert from our rotations per minute to theta per second, or angle per second,
That would be using
radians per second.
as
Yeah.
as the rotation for
Yeah, that's correct. And then you'll find your omega, and then you can calculate tangential velocity. So that's, again, a little bit of a review, but also related. This one, also a little bit of review. They're doing a linear acceleration to an angular acceleration, so you have to do that. You have to do that conversion across. Remember the chart that we made earlier with the linear stuff and the angular stuff. You're using that there, and then here is a kinematic. This is a kinematic one right here. Final angular velocity. So you have to use a kinematic equation to find that final angular velocity. You can either do it linearly, or you can use linear kinematics and convert to angular, or the other way around. You can go angular kinematics and convert to linear. But eventually you'll need to know the tangential velocity as well, so you'll have to go back and forth. But it's just kinematics. And this one is a very similar one, except it's a merry-go-round. So they're giving you radius, they're giving you and this one actually they're also combining a cat that's hanging on and has a particular force it can hang on with. So you're going to use some kinematics to figure out how fast it's going around and around, and then you can figure out how much centripetal force the cat feels compared to what they can hang on with. So this one has a lot of stuff in it, but it's just angular kinematics converting to some linear kinematics and then some centripetal acceleration.
Mr. Bailey,
Yep.
what chapter was centripetal force and centripetal acceleration again?
It was in chapter 6.
Okay.
So we're combining now chapters 6 and 9 and 10, right? And when we did 6, I don't know if you remember, but I said, I don't know why they do this here. And I still really don't know why they do this here. I would not do 6 there. I would do 6 closer to 9 and 10, or 9 and 10 closer to 6. There's only really one reason, and that is the idea of potential energy. But I don't agree with putting chapter 6 where it is. Maybe I'll change it eventually. But that's the fourth problem, is just, again, kinematics. Now this one combines torques and kinematics. You have a torque happening from that mass pulling on this wheel. It's going to accelerate the wheel, right? So an acceleration caused by a mass pulling at a distance. I'm trying to decide if you even need to do a torque with this. I don't think you actually do. Yeah, this one, they give you the mass, but I don't think you actually... Oh, yeah, you do. Because this one, you have angular acceleration of the pulley, but they give you the mass of the pulley. So angular acceleration of the pulley is going to be dependent both on the moment of inertia of the pulley and the torque that is applied by the mass. So you're going to have this one's actually a kinematics problem combined with a dynamics problem. So you're going to have torques causing accelerations, and then you use the acceleration to the torque causing rotational acceleration, unwinding something, a certain number of radians, and that's going to be kinematics, and so on and so forth. So that one's a nice one. Well, not so nice, probably, if you're the student. And here's the rolling down the hill. This is our problem with the rolling mass, right? It has some moment of inertia, and some of its gravitational potential energy is going to go into linear kinetic energy. Some of it's going to go into rotational kinetic energy. So you have to figure out how much kinetic energy is going into both.
I don't have the picture. Is that going to be a huge problem?
Yours, I'm not showing the picture.
Yeah, does that mean there's a glitch or just?
No, it means that we know now why your other one wasn't working. It's because your flash player needs to be updated.
Okay.
So.
You can just search like flash update on
Yeah.
that. Okay.
This one's a classic. You have a disk, the big disk is already spinning, so it already has some angular momentum. And then you drop a smaller disk on top of it. What do you think is going to happen? So the big disk has already got some angular momentum, it's already spinning around, and you drop the smaller one on top of it. What happens to the overall system? The rotation slows down. Why?
Because the other one's not moving.
Because you've increased its mass and mass. You've increased, what you've really done is you've increased its moment of inertia. So in order for angular momentum to be conserved, it has more mass and more mass distribution, so it slows down. This is the equivalent of putting your arms out, right, when you're spinning. So you add on another moment of inertia, another disk. This one is very similar to the one on the track, except that they want you to calculate how high it's going to go up on the other side. And they want to calculate the angular and linear velocity at the bottom of the track.
And for angular velocity, that's always on the outside, right?
Angular velocity has no outside.
Or it's on the outside of the hoop, right?
Has no outside. Angular velocity is just how it rotates. Doesn't care how big the hoop is. When you convert to linear, then it cares. Right? I'm not going to go into that because I'll give it away. So here they give you an angular acceleration, an initial angular position, a rotation time, and a final angular position. They want you to find an equation that will give you what you need, the initial angular velocity.
Equivalent of the x or the y position.
Yeah, you're solving an equation, right? This is not position, this is velocity, right? So here they're just having you find the right equation and solve for the right thing in all these equations. Well, in this one, they're actually giving you numbers, so to calculate the rotational kinetic energy. That one's easy. Also, angular momentum, easy if they give you everything. And there's some of these ones at the end aren't hard at all. Actually, I might recommend doing the ones at the end first. So go do the last ones first, and then come back and do some of those harder ones beginning. This one's not necessarily all that easy, but it's still just kinematics. Well, no, this one is the spinning skater. This is conservation of momentum. Initial angular momentum equals final angular momentum. Something changes. What else changes, right? So, that is chapter 10 in a nutshell, just like we did chapter 9 and chapter 8 in nutshells. Got a lot of nutshells, and now it's time for us to break and be done for the day. So, we will see you all tomorrow at which time we will answer questions about Chapter 10 and start Chapter 11. Make sure you get started on the homework so that you have the questions that you need to ask. All right? Yep.
So is the test on Friday set in stone?
The test on Friday is not necessarily set in stone,
Um,
but I don't want it to go too much into next week because we'll be on to new chapters. So.
Right.
Set that up with what's it called?
Yeah, you can go set up a time in the Success Center to take that. So
And it's open book again.
it is open
Uh,
book.
We'll do lab Wednesday this week. Do you think we'll continue to do labs on Wednesdays, or will we do it on Tuesday next week?
I think Wednesdays have been working better for my lecturing schedule, so probably Wednesdays. Will Tuesday work better for you?
Well, no, I was just, I just wasn't, I don't work tomorrow, so I'm gonna study and do my homework all day.
Or okay,
So I was just, but I work every day after that, so I was just trying to figure out when would be a good time for me.
okay, yeah. I think Wednesday works best as far as where we're at in the book. But if you absolutely need to do it a different day, we can. So
Okay. Well, I'll just message you if I have any questions or things to say.
okay, sounds good. Any other questions from anybody? Okay. Have a good one. We'll see you tomorrow.
Would I be able to just go over that cat problem from chapter 1? Dad, I did not touch the chips. You have to leave them here.
Take them with you if you want a snack while you're working tonight.
Okay.
Okay. I don't want them. Make me sick.